Well, hello again. Welcome. Uh, I did a rather long video yesterday that I am not going to publish because I ran into too many problems. But basically, here's the thing. I am trying to improve my virtual assistant software. Uh, and the other day I went in and I tried to uh, run some interactive scripts with using voice. So in other words, it would ask me for my first name. I would give my first name, and then it was supposed to stick it into a database. And what I was finding was that vosk was using the microphone capture was not working very well for this particular purpose. It was adding the word the to the beginning of the sentence or the name. And so then I tried deep speech. I wanted to see if that's come along much in the past year. I haven't tried it in about a year. Uh, and it wasn't very good. It was even less accurate, even though the word error rate, the quoted word error rate is about the same with my voice at least. It didn't do very well. So who knows? Maybe it does better with female voices than it does with male voices. Supposedly, vosk is better for male voices. I guess it depends on how they trained it. Uh, deep speech is, I believe, trained with their. They have some sort of an open project where you can go online and record a few things with your microphone, and it'll save it to files. Uh, I forget, Mozilla Open Speech or something like that. I don't think vosk has anything like that. I don't know where they got their voice data. Anyway, I started looking into this some more, and so I sat down and I started working with socks. Let me jump over here to the desktop, and so socks is a sound exchange, and it does a lot of things, but it's basically can be used. At least I'm using it as a command line uh, audio processing tool. So what I did was in my I created a new repository here called JulieBot, and this is up on my GitHub page if you want to go look for it. Uh, if you want to look for it, let's see, let me pull it up here so you can see it and have the URL. It's GitHub/MikeyBees, and the repository is called JulieBot right here. And I'll just keep that open for now because we may want to come back to it. So in the my controller, I've set this up so far with a module called Speak in Here. And Speak in Here has where is it? This doesn't look right. Oh yeah, all right. So I'm a little confused here. I had closed this rather than opening it. All right, so here's what's in here. I've got this convert wave to text. I've got a listen.py and a speak.py. And up here, I do a from speak in here, import speak, listen, and convert W to T, wave to text. And these are all called from my controller.py file, which is where? It's here, controller.py. So the first thing this has to do is listen. Right? If you go back to the controller.py, you'll see, let me pull it down from here. It says, what is your name? Right? So first it speaks, what is your name? Then it listens. So over here and speak in here, first we have speak. Speak.py. And this is pretty basic. I'm importing GTTS and PyAudio and subprocess here. And I'm doing a text-to-speech equals GTTS, blah, 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 saving it to an audio file called speak.mp3. And then I'm doing a subprocess call to MPG321. Now, there's a lot going on here that you don't see. First of all, I did not write this function. I had OpenAI's Copilot write it for me. So I just put in a comment saying that I wanted something that used GTTS to speak text, and this is what it gave me. And looking into this, I agreed that subprocess call is the way to go, because you can do a subprocess call or a subprocess run, and subprocess call is going to wait until the program sends back its exit, what is that called? The return code. The return code. And so it's not going to start the next item up. And it also is using MPG 321 rather than MPG 123. And so I thought, that's odd. I'd never heard of this before. I've been using MPG 123. Should I use this instead? And it turns out that the MPG 123 project was forked, and this is the fork of it, the 321. And this is being maintained, and I guess 123 is no longer being maintained. So this is the newer version of the same program with some improvements, I suppose. I don't know where those improvements lie, if it's memory handling or what, but I guess it makes sense to try to be on the most recent version of a program if it's getting support. So go back to controller.py. We call speak.speak here. And then listen.listen. And if we look at the listen.py program, if I can find it, this, I just have to get rid of these extras here. This needs a PyAudio wave system subprocess. And what this is doing here is it's grabbing, it's recording from the microphone and sticking it in a file. And this also was written for me by Copilot. It gave me several versions of this, and this is the one I chose, and it seems to work perfectly. And it makes, it uses this rate, 16,000, which is fine. And I don't know about the chunk size, if I should change that at some point. I don't know. Anyway, this comes back, and it gives a file called listen.wave. And I can play it. At least I think it's called listen.wave. Michael. All right, so some things about this file. First of all, there's a lot of noise. Second of all, there's a large amount of silence before I say my name. And then there's a large amount of silence that follows it. So I thought, all right, this is not great, but this is what the microphone is sending to the Caldi recognizer. Can I improve this? So I started doing some research on it, and that's where this sock stuff comes in here. I found this interesting article called The Socks of Silence. And basically, it's possible to trim off the silence at the beginning of the wave file. And so how did I do that? Probably the easiest way is to show you the code. And that would be in controller.py. So it asks me for my name. It listens for me to say it. And then I get this listen.wave file. And so once again, I use subprocess.call because I don't want anything else to happen until this is done. So this is, it's like using joined threads, but this is not, I think this is better than joined threads. I can't tell you exactly why, but I think it is. I'll have to do some more research on that. Anyway, we call the SOX program. We pass it the listen.wave file as the input wave. Then reverse.wave, this is going to be the output file that we create. We're going to trim the silence. I'm not sure what these numbers do exactly, but then we're going to reverse the file. And then we end up with a file called reverse.wave. And if I play, you'll hear that the silence at the beginning of the file is back. Right? The silence before I start talking is, I don't know, it's like a second or 2 seconds of silence. And then I talk. And what I'm saying here is backwards now. And so why did I do this? I did this because I want to run the SOX silence.wave, speech.wave, oh, here it is. This one, silence.wave, reversed, right? So we went from listen.wave to reverse.wave to silence.wave, right? So let's play that. Michael. Now you'll see that all of the silence has been taken off. Right? The silence at the beginning, the silence at the end. The file has been truncated to only include when I'm speaking, which is great. And then it still has noise in it. I'll play it again. Michael. Right? It has that hissing kind of noise. You might not be able to tell because you're hearing that over the microphone, and the room that I'm in has a big fan that's running on the computer that's making that noise. So it may be difficult for you to tell, but I'm going to get rid of that. And I had to create this speech.noise profile. And the way I did that was I recorded the room, the ambient sound in the room for a couple of, few seconds. And then I ran a command. Let's see if I can find it. Control R. Let's see what happens. I'm not sure which one of these is the one that worked. All right, I think this is the one that worked here. Socks noise.wave -n trim 0 1.5 noise prof speech.noise profile. And what this did was it created this noise profile file. And if I cat that, speech. Am I in the wrong? What am I doing here? You'll see that it's got a whole bunch of numbers in here. I'm not at all sure what these are, but once you have this speech.noise profile, what you can do is you can do this process call, socks silence.wave. This is the one we just listened to. Right? We listened to this silence.wave. Michael. This is the input. The output is speech.wave, or whatever we want to call it, final.wave, however you want to say that. We use Noisard as our switch, and we pass it the speech.noise profile. And then this number here says how much we want to apply this. And what happens is we end up with speech.wave. Michael. I don't know if you can tell, but I can tell here that has that hissing noise removed. It's much clearer. So the thing is that now we have a wave file that has the speech that we want to have converted to text. So what do? Well, our controller then I had a bunch of code. I'm sure that I had a bunch of code. All right, I've got another file here. Did I not save it? Did I put it in speak in here? I thought I had a file called recognize that I was working on last night at 3 a.m. Well, I'm not seeing the code, so I don't know what happened to it. Unless I stuck it in the wrong directory. Let's see if I can find that code. And I may have, well, this is basically the code before it. This vosk API Python example test ffmpeg.py. And I don't know what happened to it. It should be in my, it should be somewhere in that project, and it's not showing up. But basically what we're doing here is we are creating a model, creating a synthesizer here, and we're starting this process where we're running ffmpeg. And this is a command line tool that runs, it will play WAV files and all other kinds of files, and it will allow for all kinds of conversion. So for example, if I wanted to change the sample rate, I should be able to do that there. Anyway, what this is doing is it's sys.argv1 can be replaced with the file name speech.wave. And so it opens the file and it creates a pipe and it sends it into this data object here. And then the data object goes through this synthesizer here, which creates the text. And I'm not going to spend a lot of time with this because this is the wrong way to go. Every time this runs on a file, it has to start up the Kaldi and load the Kaldi recognizer. So it's very slow. However, what it does do is operate with more accuracy because the sound has been cleaned up. It's been put into a format that's better for the recognizer. All right, so that's a problem. So what's the solution to that problem? Is there a solution to that problem? Well, I think there is. Alpha Cephi has vosk server. It's a GitHub project, and it's pretty easy. You clone it, and then you run it. Actually, I don't think you even have to clone it. You just run this command, and if you have Docker installed, which I have, you run this command, and it will pull down the AlphaSep Kaldi en Docker container and run it. And then there will be a web service running on port 2700 on your machine. And I don't know, I may have to open up a port for it. Probably not, because it's on the same machine. But if it were on a different machine, if the different machine than my client software, I'd have to open the port up through my firewall. But because these systems nowadays all have their own local firewalls, and once this is up and running, I haven't tested it yet. Once it's up and running, it will run continuously. So it won't have to load anything every time I give it something to convert from a WAV file into text. I think this is the way to do it. I'm going to work on that today. But that's the state of the art right now for this project. I'm hoping that this, by removing all of that, I guess it's an oxymoron, noisy silence at the beginning of my speech, the recognizer should do a better job and produce the right text. And then, if this works, I'll be able to create those interactive scripts that are giving me a problem, or that were giving me a problem. So the combination of using subprocess .call and running the Kaldi server and creating individual WAV files and then cleaning them up may be the best architecture that I can come up with for this particular use case. Anyway, that's the state of the world, and I thank you for joining me. Bye-bye.